I'll be talking about the relationship between the displacement of an object from its point of origin and its initial velocity times time plus 1/2 times its acceleration times time squared. So the first part of the equation that you see here represents the displacement of the object were it to continue at its initial velocity, and the second part here represents its displacement due to acceleration. So by combining these two, by adding them, you get the total displacement, which is represented by delta x. And this relationship only works if acceleration is held constant. Here you can see a pretty standard velocity versus time graph. It's parabolic and could represent a whole variety of different situations, the simplest probably being an object being thrown up into the air and coming back down right to its point of origin. This graph here is the graph of the derivative of the last graph that you saw in the last slide. And if you take the definite integral of it, then it's a triangle. And the area of a triangle is 1/2 base times height, as we all learned in geometry class. So in the context of this problem, the base is time and the height is acceleration, which is where you get 1/2 AT. And this definite integral gives you an average velocity because meters per second squared times seconds gives you meters per second. And when you multiply that by time, when you multiply the average velocity by time here, that gives you meters per second times seconds, which gives you meters, and that's how you get the displacement due to acceleration. And that's where the part of the equation 1/2 AT squared comes from. So this here is what I was explaining on the last slide, except written out in numbers and letters. So velocity times time here gives you meters per second times second, which gives you meters. So that's your displacement were the object to remain at its initial velocity. And here is the 1/2 AT squared, which is 1/2 AT times t, which is the average velocity times t. And this is where you found 1/2 base times height, the definite integral of the graph of acceleration versus time, which is where you get the displacement due to acceleration. So here you can see a depiction of the off-the-roof lab that we did earlier this year. This here represents the ball's path to the ground, and this is the y direction, and this is the d direction, because I didn't want the x in the equation to throw you off. It's not really talking about what we typically consider to be the x direction. It's just the displacement. So if you analyze each direction and you look at the d direction, it doesn't have any acceleration, but it does have initial velocity. So this part of the equation becomes unimportant because acceleration equals 0. And it continues to move at the same speed, so when you multiply it by time, you have the distance that it's traveled. In the y direction, there's no initial velocity, so this part becomes unimportant. Because if it kept moving at its same initial velocity, it wouldn't move at all. So all of the distance that it travels occurs because of acceleration. When you combine the two, both parts are important because you have initial velocity in the d direction and acceleration in the y direction. So you combine them to get the total displacement of the object. So that's all I have to say about this topic. Please enjoy this super artistic ending slide and have a wonderful day.